Puedes comenzar.
Bueno, bueno, primero que nada, para poder participar en este webinar y bueno, también a los organizadores por el esfuerzo que han puesto, yo creo que desde el comienzo, muy, muy valorable. Así que bueno, sin más preámbulos, hablar sobre la emisión de señales acústicas codificadas, la estimación de tiempos de vuelo en zonas de posicionamiento subacuático. Mi nombre es Santiago Murano, soy magíster ingeniero de la Universidad Nacional de la y actualmente soy doctorando en esta universidad y en la doctorado en electrónica. Soy docente de investigación en la Facultad de Ingeniería de la Universidad Nacional de la Paternal de San Juan, Información y Sensores, el grupo HIPIS. Y también he colaborado en el grupo de la Universidad de Ingeniería Electrónica Aplicada, Espacios Inteligentes y Transporte. Bien, la de hoy estará dividida en las siguientes... el índice, perdón.
César, tienes que pasar la diapositiva.
Dividido en temas, un poco lo que es el sistema de posicionamiento subacuáticos y sus aplicaciones, por qué es necesario calcular las señales. Luego les comentaré un poco sobre el modelado y veremos algunas simulaciones y pruebas experimentales que se han desarrollado en este entorno y bueno, y después comentarles un poco sobre una plataforma donde estamos realizando también en MATLAB para aplicación del entorno subacuático. Siguiente, por favor. ¿Qué más similar al que utiliza los sistemas de GPS? Siguiente, que están compuestos por boyas o balizas sincronizadas de los satélites, y esto les permite ideas codificadas de forma que se encuentren por debajo de la superficie del agua para que estos puedan obtener su posición. Es por ello que el sistema de GPS, como trabajan basados en emisión de señales electromagnéticas, obviamente a los pocos metros de la superficie del mar, con lo cual no permiten posicionar objetos o vehículos por debajo de unos pocos metros. Entonces, a cada una de las boyas se les asigna una única señal, lo que permitiría que el vehículo tenga posición a través de recibidas, similar a lo que haría un teléfono recibir señales de los satélites GPS. Por otra parte, estas boyas estarían sincronizadas a partir de las señales de reloj que obtienen de las señales de GPS. Siguiente, por favor. Esto principalmente debe o nos lleva a la integrar señales apropiadas para poder realizar la detección de tiempo de vuelo que nos van a permitir posicionar posteriormente. Siguiente, por favor. como comenté, básicamente es de posicionar vehículos autónomos o redes de sensores o de equipamiento de navegación en lo que serían, por ejemplo, la industria de gas y petróleo offshore o el relevamiento o así también como exploraciones científicas. ¿Por qué es necesario codificar Bien. Primero porque permite la acción simultánea de múltiples balizas, lo que lleva a un esquema CDMA, que sería el de acceso múltiple por código. Para ello se requiere de utilizar códigos con buenas propiedades de correlación. ¿Qué quiere decir esto? Que se requiere un código que al correlarlo consigo mismo, al autocorrelarlo, presente en su señal resultante de la correlación un pico elevado con una amplitud determinada E y lóbulos laterales lo más mínimos posibles. En cuanto a la correlación cruzada, lo interesante o lo esperado de unos códigos con buenas propiedades de correlación es que en el instante de llegada no haya, o sea que sería para el retardo cero que se ve ahí, no haya ningún pico. Esto nos estaría indicando que estas secuencias o estos códigos tienen buenas propiedades de correlación para un esquema de emisión simultánea. Siguiente, por favor. Hasta donde se permiten mejorar la estimación, ahí. Entonces, estos códigos, ahí, gracias. Estos códigos entonces permiten mejorar la detección de la señal en condiciones de SNR o de relación señal a ruido muy y nos van a permitir mejorar la estimación de la posición, incluso ante efectos indeseados del canal. Ahora sí, siguiente, por favor. Bien, la medida de tiempos de vuelo, ¿qué es? Bien, se puede separar en dos sistemas posibles. Aquellos sistemas que tienen sincronismo, es decir, que tanto el emisor como el receptor están sincronizados como GPS. Lo que consiste es en la medida que viene del inglés flight o time of arrival. A partir de las medidas de tiempo de vuelo se separa de trilateración con 3 o más emisores con los cuales podríamos obtener luego la posición. O y la diferencia de tiempos de vuelo. Esto nos va a permitir determinar, o mejor dicho, de esto, todo conjunto con buena edificación, es la determinación de un instante de tiempo con la mayor precisión posible. La señal, en el caso de las cosas o del entorno acuático, es una señal acústica. La señal viajará a través del medio hasta llegar al receptor. Si el receptor conoce el instante en el que se emitió la señal, podrá obtener el tiempo de vuelo en el agua conocida. Podríamos de esta manera obtener la distancia de separación entre el transmisor y el receptor. Y cuando conozcamos el instante de tiempo en que el emisor hizo la emisión. O sea que estamos hablando de un sistema con una diferencia de tiempo de vuelo en la que se requiere por lo menos un emisor más. Siguiente, por favor. Existe una gran variedad de bastante amplia de aspectos. Yo principalmente en el trabajo de la tesis de doctorado, en lo que me he enfocado y un poco lo que he estado investigando en los últimos años, es sobre el uso de secuencias ZADOFF CHU, que pertenecen al grupo de secuencias polifásicas. Presentan propiedades de autocorrección y buenas propiedades frente al efecto Doppler. Que en este caso son secuencias reales con elementos aleatorios y valores pseudo-aleatorios, que también presentan modalidades de correlación, aunque frente al efecto Doppler ya no son como en el caso de las secuencias Chu. Siguiente, por favor. Estudiar y bueno, se ha hecho la ZADOFF CHU respecto al efecto Doppler. Para poder transmitir esta secuencia o este código es necesario modular la señal que se va a transmitir para poder adaptar la secuencia del canal y del transductor. Para eso se utilizan esquemas de modulación. Bueno, se han hecho pruebas con moduladores tipo QPK, tradicionales, FDM. Sí, por favor. Y a la siguiente también. También es el de OCDM, que es una expresión de código, en el que consiste que a cada secuencia a transmitir se la modula utilizando también un símbolo. Se la modula utilizando chip, que en distintos instantes de tiempo. Entonces, de esta manera se logra obtener un símbolo, como que se ven en el gráfico de la S5 ya de que se tengan. Y se modulan codificando o modulando, perdón, el código para ser transmitido al canal. Otro de los esquemas es o se han propuesto dos variables y slow frequency hopping. Este esquema consiste en la emisión, la emisión de las secuencias, realizando un entrelazado y siguiendo un patrón de saltos en frecuencia. En el gráfico de la izquierda vemos en el eje Y la frecuencia, las distintas horas de frecuencia que se están asignando a cada uno de los emisores B1, por ejemplo. Entonces, el esquema slow frequency hopping, que es en el en el caso de tener una secuencia de longitud 7, por ejemplo, se envían todos los elementos, o sea, los 7 elementos de esa secuencia, modulados en la portadora F1, para el caso de la baliza 1, esa portadora, que es la frecuencia 2, luego la siguiente, que sería la frecuencia 4, y así siguiendo el patrón de saltos. Y lo entrelazando. En el caso de frequency hopping, lo que se hace es, de vuelta en el en todas las portadoras, en cada salto de tiempo, según la duración del símbolo, y a continuación se emite el segundo elemento nuevamente en todas las portadoras, así el tercero, el cuarto y el quinto hasta completar la secuencia. También, en búsqueda de obtener secuencias lo suficientemente robustas al canal. Siguiente, por favor. Tenemos ya el esquema el modelado del entorno, que muchas veces uno ve al mar como un entorno agradable, pero no lo es todo lo contrario, es bastante activo y con las señales, sobre todo las señales acústicas. Siguiente, por favor. En este caso, han creado un modelo basado en el trazado de rayos, que contempla la fenomenología actual de este entorno, en el que se configuran parámetros de tanto como del esquema de comunicación a utilizar, y permite desde el emisor al receptor trazando los rayos por donde iría incidiendo cada uno de los supuestos, digamos, por donde se propaga De esta manera se pueden obtener las distintas llegadas de la señal rebotado tanto en la superficie como en el. Se puede ver en la captura de un ejemplo de la salida del trazado de rayos. Donde tenemos el emisor a la izquierda, TX, y el receptor a la derecha. ¿Cuál es? Siguiente, por favor. De esta manera, el entorno, lo que habría que cargarle sería el perfil de velocidad del sonido, perdón, el perfil de velocidad del sonido, por propagación en la rebotes tanto en superficie como en el fondo del mar, y efecto dinámico de las olas. Se produce un ensanchamiento Doppler o el desvanecimiento, cambio de amplitud y fase. Siguiente, por favor. Hay que cargarle al modelo lo que es la densidad del agua y del fondo, las velocidades del sonido en el material del. Sí. La temperatura a lo largo de la columna de agua o el perfil de velocidad del sonido, la salinidad, por ejemplo, un ruido blanco gaussiano, el perfil batimétrico que nos va a permitir obtener los rebotes en el fondo, y por supuesto la velocidad en la superficie, lo que nos va a determinar la altura de la ola que se produce. En cuanto a los parámetros del sistema, lo que se requiere es en tres dimensiones de los emisores como del receptor, puede cargar también la frecuencia del traductor o el idioma, como digamos, en una función que afectaría si transmitida. También haría la emisión, y otro de los datos a tener en cuenta es la velocidad a la que se mueve bajo, entre transmisor y receptor, o evaluar el efecto. Siguiente, por favor. Bien, esto es lo que les comentaba recién. La siguiente, por favor. Aquí hago un paréntesis. Digo, bueno, salimos del agua por un momento. Pequeño paréntesis durante la presentación. En un estudio de hornos en interiores. Entonces, de un tiempo estuve investigando justamente distintos esquemas de codificación y modulación, comportamiento tener el posicionamiento a través de señal de EPS. De esta manera, lo que se obtiene es una comparativa también de estos códigos con distintos esquemas de modulación frente a los diversos efectos del canal, el camino, el ruido blanco gaussiano, el efecto lejos, ruido impulsivo, el efecto propio de los transmisores y del micrófono, e incorporar el movimiento. Sí, por favor. En este caso, entonces, se han hecho pruebas tanto en simulación empleando este modelo como pruebas en entornos reales, digamos. Algunas de ellas fueron pruebas en estático, donde está en el suelo, y de esta manera ir cambiando la posición del micrófono y, bueno, determinar, tratar de estimar las posiciones a partir de las medidas de tiempo de vuelo de las señales emitidas por los emisores que estarían en el techo. Entonces, bueno, se han hecho pruebas experimentales en posiciones fijas y conocidas. Siguiente, por favor. Luego se han hecho pruebas en movimiento, donde se ha utilizado una plataforma forma giratoria en la que se un observador constante, posiciones conocidas, con el cual íbamos a utilizar como referencia de la estimación de la posición en cada instante, digamos. En este ejemplo tenemos la baliza en el y a la izquierda, por favor, vamos a ver una captura, digamos, de cómo se obtienen ya las posiciones en el eje X e Y, posiciones obtenidas una revoluciones por minuto. En este caso se pueden observar, digamos, las diferencias que existen entre las posiciones reales, que sería el círculo negro, y los distintos puntos, que son las posiciones estimadas. Pero bueno, esto es lo que se trata de corregir, luego incorporando las secuencias ZADOFF CHU, reemplazando las secuencias Kasami. Siguiente, por favor. Bien. Han realizado pruebas utilizando una red real, con el cual tiempo de resultados. Y aquí lo que vamos a observar es una gráfica de función de ambigüedad, donde se representa el pico de correlación para los tiempos en t igual a 0, que es cuando se detecta la secuencia, se ve ese pico de correlación, y así cómo se va desplazando el pico de correlación a medida que el receptor se va alejando del emisor en este slider lineal. Entonces lo que se puede observar que para la secuencia ZADOFF CHU el pico se va atenuando, pero siempre es posible que se va a ser una figura a la derecha, a ver, el mismo gráfico, pero para las Kasami. En este caso, a medida que empieza a aumentar la velocidad del micrófono, llega un instante en el que se pierde el pico de correlación y ya es posible detectarlo, y recién vuelve a aparecer una vez que el micrófono llega, digamos, al tope y se detiene en el otro extremo. Con lo cual, de esta manera podemos ver las ventajas que presenta la secuencia ZADOFF CHU frente a otro tipo de secuencias. Bueno, regresamos al agua nuevamente y ahora sí, les comento rápidamente, pues ya estamos medio justo de tiempo. Siguiente, por favor. Bien. Entonces, toda esta experiencia de pruebas que se han realizado en inglés, se intentó replicarlo en entornos subacuáticos, con lo que en principio se comenzó con realizando las simulaciones en estos entornos y adaptando el modelo para realizar las pruebas en aguas poco profundas de las zonas patagónicas de la universidad en la que trabajo, de Argentina, de la provincia de la ciudad de Comodoro Rivadavia puntualmente, los parámetros al entorno de estas aguas. Siguiente, por favor. Siguiente. Indicado en el modelo, se han realizado pruebas en cuanto a en emisiones, pero en este caso en el canal, en el entorno subacuático, considerando el receptor en movimiento y como una instancia, una velocidad. Entonces, de vuelta, en aire y analizar su comportamiento ahora en agua, encontrando resultados similares. En la gráfica que estamos observando acá, se puede ver cómo a distintas velocidades va aumentando el error absoluto y esto indica que el pico de correlación se está desplazando en el tiempo a medida de distancia, que posteriormente se convertirá en una posición con... Bien, aquí lo que vamos a ver entonces es nuevamente tenemos dos esquemas de modulación, perdón, para el segundo esquema de modulación, el QPSK y el OFDM, que son las dos figuras de arriba, modulada con el esquema PSK. Entonces, la ambigüedad, en este caso, también simulado en el modo subacuático, y donde se puede ver nuevamente que para las secuencias Kasami, la amplitud del pico de correlación se ve para cierto rango y donde empiezan a aparecer ciertos lóbulos que pueden perjudicar la correcta detección del tiempo de vuelo y posteriormente de la posición. Sí. Frequency hopping, vamos a ver que las de slow también bien, laterales, y para el caso de la fast frequency hopping tiene un efecto similar al de las secuencias Kasami, pero sí que empieza a aparecer un pico de correlación que a velocidades mayores e empieza incluso a superar el pico principal, la principal, con lo cual este esquema se ha descartado por completo. Siguiente, por favor. En cuanto a pruebas experimentales, en este momento lo que llevamos realizado son pruebas pruebas en una piscina, aunque las distancias son cortas y no son, obviamente no tienen tanto que ver con las pruebas que se pueden realizar en el mar abierto, pero sí es un entorno que tiene mucho rebote, producto de las paredes cercanas, digamos, lo cual también varios errores. Entonces, en este son pruebas del emisor y el receptor a distintas posiciones, aprovechando el espacio dentro de la piscina, pero acá no podemos podido determinar el efecto Doppler por el movimiento de algunos de los emisores o del receptor. En un principio se han realizado pruebas de punto a punto, digamos, entre un emisor y un receptor para determinar la distancia de separación entre ellos. Y bueno, para una distancia de 3 metros han logrado errores de 4 milímetros. Obviamente, digamos, porque es un entorno mucho más amigable que el mar. Siguiente, por favor. Sin embargo, al momento de pasar a entornos abiertos, nos vamos que varía en el tiempo. Entonces, así como el viento, la temperatura, distintos parámetros, digamos, que van a ir afectando al modelo. Una de las cuestiones también hay que considerar que es el ground truth, que es la trayectoria del modelo en movimiento. Es sincronizado detector, salvo que sea una conexión cableada, si no también es un de obtener, ya que señal de sincronismo, vemos lo mismo, estaría haciendo algo similar a lo que hacemos cuando intentamos detectar la relación. Bueno, es una deriva, un error que se da con empleando estos dispositivos. Habría que tener un cierto control sobre el tiempo que está sumergido el vehículo para no acumular demasiados errores, y bueno, etcétera. Siguiente, por favor. Y ya para finalizar, les voy a comentar, mostraré muy brevemente educativo, que es de modelo a un entorno gráfico y un poco más amigable, basado en en la cual van cargando todos estos parámetros y hacer pruebas de simulación, y la idea es que posteriormente se puedan cargarlos en la aplicación del computador y poder evaluar las posiciones obtenidas a partir de aplicar ciertos algoritmos. La herramienta nos permite en una primera pantalla elegir el código a utilizar. Siguiente, por favor. A utilizar es, bueno, configurar los parámetros de emisión, la cantidad de emisores que tenemos, la frecuencia de portador a la que se va a trabajar, el tipo de transductor a utilizar, si la emisión, es decir, un esquema CDA o multiplicado en el tiempo, un TDMA o un híbrido de ambos. Distintos parámetros, y podemos obtener también distintos gráficos de salida o generar señales para almacenarlas y luego hacer las pruebas reales, etc. Siguiente, por favor. También permite cargar el modelo batimétrico del perfil topográfico, digamos, perfil del fondo, la posición del receptor, y como configuraciones avanzadas todos los parámetros que había mencionado anteriormente. La salinidad, la densidad del agua, del material en el fondo, del pH, del viento, etc. E incluso si el vehículo el sector está moviendo. Siguiente, por favor. Devolviendo otras ventanas de resultados, como el trazador según los cargados. Está en etapa de finalización, pero bueno, es algo que nos permitiría hacer varias pruebas a nosotros, y además que si esto podría estar compartido de forma libre, digamos, para que se utilice siempre citando a bien. Aquí se puede ver, digamos, el resultado del trazado de rayos. Siguiente, por favor. Las correlaciones que se hacen tanto en banda base como en distintas etapas de la escala ya modulada, o los instantes de llegada, porque el mismo modelo conoce, puede decir en qué instante de los rayos, y determinar luego el error que existe entre la animación obtenida y la posición real, digamos. Y bueno, también podríamos observar las cosas que tienen con las distintas llegadas de los distintos emisores, como van llegando, dicen el tipo, debido a la distancia que existe entre cada uno de ellos. Determinar el gráfico de correlación, por favor. A partir del gráfico de correlación se puede determinar entonces el tiempo que tardó en llegar esa secuencia a partir del pico, que ya no es algo tan claro como se veía que vimos al comienzo. Para la primera llegada en arriba, podría obtener del tipo de vuelo, los algoritmos de modulación o multilación, realmente una posición estimada a partir de estas señales. Entonces, de modulación y empleando los modelos subacuáticos, digamos, anteriores, como el subacuático, podemos evaluar el comportamiento de estas señales para utilizarlas en el cálculo de una posición de un vehículo que está bajo de la superficie del agua. Siguiente, por favor. Y ya para conclusión, digamos, como conclusión de trabajo futuro, bueno, se puede haber determinado, digamos, que tanto en aire han dado resultados que permitirían mejorar la precisión en la detección de estos tiempos de vuelo, y en agua lo mismo con el uso de ZADOFF CHU, gracias a sus propiedades de vibración. Incluso es posible compensar el efecto Doppler utilizando frecuencias. Siguiente, por favor. En entornos ciertos y bueno, puede tener una conocida a partir de sistemas especiales, la estimación de la profundidad de presión. Bueno, esto sería todo. Para realizar la presentación aquí en el webinar. Les agradezco a ustedes nuevamente por el esfuerzo que están llevando a cabo para que sigan existiendo estas presentaciones en que estamos hoy.
Muchas gracias a ti,
Atento a la consulta.
Santiago. Sí, gracias. Nosotros te agradecemos por aceptar la invitación y por tu tiempo, porque compartiste tu tiempo en este evento. Muchas gracias. Y bueno, en honor al tiempo también no vamos a hacer la sección de preguntas y respuestas y vamos a pasar a presentar a nuestro siguiente ponente. Gracias. Bueno. Hasta luego, gracias. Okay, our next speaker is the Dr. Todd Morrison. Do you hear me, Todd?
I can hear you.
Okay.
You can hear me.
Yeah. Dr. Todd, I'm going to say a few words about you, and then you can share your slide. Okay?
Mm-hmm. I'll be ready.
Okay. Dr. Todd Morrison is a senior ocean engineer at the Woodhull Group. In 1997, he was awarded a PhD in oceanographic engineering by the Massachusetts Institute. His degrees and experience have focused on instrument development, the design of oceanographic systems, and underwater vehicle control. At Woodhull Group, he applies nearly 40 years of experience with electrical and electronic system and design, mechanical system, material science, and software development to design, fabrication, and installation of complex oceanographic instrument systems. This experience also includes design, deployment, and recovery of data collection systems in support of proposed offshore wind energy projects. Okay, Todd, you can share your slide.
Okay, I will try. Okay, can you see my title slide?
Yes, I see.
Great. Okay. Greetings, everyone. Thank you for the fine introduction. And is this going to work? There we go. So, thank you very much for inviting me. A quick outline of the talk. I will try to address motivation for some of the things I do. I'll be talking about the outcome of a government mandated program in the US. I'll try to describe the environment we're working in, both the environment and our working environment, the evolution of the systems we have designed to make measurements, a little bit of data analysis and results, I will convey a secret towards the end, and hopefully get to some conclusions. I wanted to let you know that I have actually been in Guayaquil before, about 14 or 15 years ago. I tried not to talk too fast in English, but I am not sure I always succeeded. And if I go too fast, please slow me down. I love being interrupted. I also like to tell stories, and I'm sure there will be a few stories in this talk, and I hope you enjoy them. I did learn a little Spanish when I was in Guayaquil, not enough to give a talk, but I was able to get by with 5 very important phrases, somewhat to the chagrin of my daughter, who was about 14 at the time. But the 5 phrases I learned and depended on were gracias, por favor, de nada, café con leche, and cerveza. So motivation. And by the way, can everybody hear me clearly? Yes?
Yes.
I can't hear anybody, but I will hope you can hear me. This is a quote from Isaac Asimov,
Everything is okay.
author. Oh, good. Okay. I have always found this to be, in a way, about what I do and what I, as an engineer, this is the kind of thing I like to be able to provide. And Asimov said that the most exciting phrase to hear in science, the one that heralds new discoveries, is not Eureka, I found it. You know, big deal, you found what you were looking for. The most exciting thing is, that's funny. It's when you're doing an experiment or making observations or making measurements and something you're not expecting happens. And if you're a good engineer and a good scientist, you're prepared for that interesting, head-scratching moment where something you didn't expect happens, and now you can try to figure out what it is and what's going on, and that gets exciting. And so here's the first story. This is not really about the program I'm going to tell you today, but I think it's a good example. The picture here is a moored profiler. It's something I had a major hand in developing about 20 years ago. It's, as you can, there's some line drawings on the left, but on the right is serial number 0 of the profiler's commercial version. The original was developed at Woods Hole Oceanographic. And this is simply a robot. It crawls up and down a cable. The cable could be 2,000 meters long in the ocean. It carries a current meter and a CTD. And it replaces, in many ways, a research vessel that's doing CTD casts, which can be very expensive. The robot, the profiler, can go up and down once a day or hourly or once a month, whatever you want to do. And here's the interesting thing that happened when an early version of this was put out. For many decades off of Bermuda, oceanographers were able to send out the research vessel Weatherbird once a month, but that went on for years and years and years, even decades. And once a month, they could go out to a spot and do a CTD cast and see what the profile of salinity and temperature looked like. And, you know, they found some things, and that was interesting and all very well and good. And it was a very nice time series. And then the profiler was invented, and they put a mooring out at that spot and had the profiler go up with a CTD once a day for a year. And then they looked at the data, and what they found was at 1,000 meters down or 1,500 meters down, these eddies propagating through that site. They had never, ever caught one of those with the once a month sampling, but they saw many of them when they were able to go up and down once a day or twice a day. So this new technology, which engineers, including myself, was able to provide, allowed us that eureka moment, or not eureka, but that's funny, I found something new. And that's a very important thing, I think, to be able to do. And as ocean engineers, that's the kind of thing one can hope for in a career, that you can provide that head-scratching, that's funny moment. So on to what I am talking about today. I'm sure you recognize the Gulf of Mexico. This is the bathymetry. Can you see my cursor moving around? So we've got Florida over here, Louisiana, New Orleans, the Mississippi Delta, the shallows in here. This feature is called the Sigsbee Escarpment, and that's the fairly steep, as ocean bottom goes, plunge into the Gulf of Mexico. This is the loop current. This picture is showing sea surface height. The range here from the very dark area down to these blue and purple areas is more than a meter difference in significant wave height. And what you're looking at here, physical oceanography, is currents coming up from the Caribbean, forming here. This is really a western boundary current. It's the North Brazil current that comes up into the Caribbean and then sort of disperses and reforms. But it plows through here between Yucatan and Cuba and makes an enormous loop into the Gulf of Mexico and then exits under Florida and becomes the Gulf Stream. So this is the beginning of the Gulf Stream. Right now in this picture, it's pinching off an eddy. And what's going to happen, if you can see my cursor, is that this loop current, is going to connect here, and the loop current's then going to shoot out here and become a Gulf Stream, and this eddy is going to start rotating. Well, it's already rotating, but it's going to rotate on its own and gradually propagate off to the west. Here's the previous eddy. Here are counter-rotating eddies. And the really important thing to be aware of here is that these loop current and loop current eddy speeds can regularly exceed 4 knots in the ocean, which is an unheard of speed. They are really, really fast. And why is that important? This is a map of the more or less current lease blocks in the US Gulf of Mexico waters. The government leases these out. Oil companies pay a lease fee. They install platforms and they put in oil infrastructure for extracting oil. They drill holes, they pull the oil out of it, they pull natural gas out of it. We're all familiar with this kind of thing. Perhaps what you didn't know was just how much infrastructure there is in that area. More than 3,000 active wells. These are sat on by gravity platforms in relatively shallow water. As you move out deeper, tension leg platforms, semi-submersibles, giant drill ships, enormous assets, 25,000 miles of active pipeline in the frame of that picture, another 18,000 miles of out-of-service pipeline. And as much as I would like us to be going to alternative energy, wind and solar and all of these things, that kind of infrastructure has to be protected from damage. And if you've got something that can come by and it's moving its position as well as its speed at 4 knots, which can do an awful lot of damage to things like this, it's important to try and protect that infrastructure. So back about 15 and more years ago, the US government sent out a series of notices to lessees, NTLs. These were coming from what was then MMS, the Mineral Management Service, that later, after the Deepwater Horizon disaster, was split into the Bureau of Ocean Energy Management and the Bureau of Safety and Environmental Enforcement. But however, whatever bit of alphabet soup coming out of the US government it was, they started a program that said all oil and gas installations that are operating in water depths greater than 400 meters, so well out on the shelf and near the 6B escarpment and into the deep water. But all of these installations have to provide in near real time to a government public database speed and direction profiles from near the surface down to near the bottom or 1,000 meters. And if it gets much deeper than, say, 1,100 meters, I think the figure is, you've also got to do near bottom measurements, although those don't need to be delivered in real time. And what they're looking for are 20-minute ensembles, and these are reported to NDBC, the National Data Buoy Center, in near real time. Okay, so this is a drill ship. This is the West Auriga. We have a system on this ship. This is the operational environment for these current measurement systems. And to give you an idea of how big this is, again, I hope you can see my cursor. This here is an 85 metric ton crane. Here's a helicopter landing pad. This module up near the front, it goes down into the hull, is a 7-story hotel and office complex. The rest of this is involved in drilling. The overall length of this ship is about 230 to 250 meters. Engine room back here, the derrick for the drilling, and we place actually on the other side of this ship, but up at about this level, a current meter system. Well, let me just go on to the next slide. I just want to make the point that drill ships are not like research vessels. I do not know how many of you in the audience have gone out on a research cruise, but the specs for a drill ship are very different. There are anywhere from 150 to 250 people on board working 24 hours a day. They are carrying and deploying up to 15 kilometers of drill string and riser. Research vessel might be $10,000 a day, $500,000 US a day for the day rate, and there's probably another $500,000 a day in operating costs. There is no working deck down close to the water the way we might be used to on a research vessel for making measurements. I can assure you that oceanography is not the focus of anybody on board except you if you are doing this work. The rig just wants you to finish the maintenance or whatever and leave, except when they need your help. So here's a little side story. I received a call from one of these rigs, the well site leader, quite irate. This might be 5 years ago, and called me up in the morning at work and Todd, you have to come fix the system, this current meter system, and I'll show you what is involved in that. It's broken. Mike, tell me, how is it broken? I don't have time to tell you, just get out here. Can I talk with the electrical technician? No, they've been working on it for 12 hours and they can't fix it. I'm thinking, of course they can't fix it. It's not their system, it's my system. I can fix it. Let me talk. No, you've just come out. All right, fine. I went home, I packed a suitcase, I went to the airport, I caught a plane, I made it as far. I live in Cape Cod in the northeast part of the US, and I needed to be down in the south central US. I made it partway down the East Coast that morning, that day because of a late flight. I managed to get all the way down to Louisiana early the next morning on a kind of emergency flight. I got on a helicopter, I flew out to the rig, I put on my safety gear. I went down to the engine room. There's a crowd down there saying, oh, thank God you're here. Can you fix it? We can't see any of the data. What's wrong? And I walked over to the computer in the rack and turned on the monitor and asked them if they could see the data now. And that fixed it. And it took me 2 more days to get off the rig and fly home. So a 4-day trip to turn on the monitor. Interesting things happen when they really need your help or think they do. These are huge, the ships, 230 meters overall. Typical research vessel, maybe 30 to 50 meters. I think the biggest RV I've ever seen was one of the Japanese ships at 100 meters. And then one of the interesting things is You are not allowed to go out on these rigs, semi-submersibles, drill ships. You're not allowed on the helicopter, none of that, unless you have passed an enormous number of safety qualifications. And you're with your personal protective equipment, PPE, it's absolutely required, no exceptions. And I would like to show you one of the things we have to do training with every couple of years. All right, and this is helicopter underwater egress escape training. And this happens in a swimming pool at a facility. What you're looking at, this device here in blue is a simulated helicopter passenger compartment with chairs. And there's a safety diver here and another safety guy here, and then those of us being trained. And what we have to do is sit down in the chairs and strap ourselves in to a 4-point seatbelt restraint. And then they raise this thing up over the swimming pool and drop it in, and it floods and submerges. And we have to hold our breath and push out the windows and undo the safety belt and not get lost and get out of the window and come to the surface, which doesn't sound too bad. But after you've mastered that with 1 or 2 dunkings, when they drop it in, they turn it upside down. You can see that these chairs are upside down. They flip it over. And on occasion, they will even drop it into the water and flip it over and turn out the lights and see if you can still get out. And don't worry, the safety divers make sure you get out. They're in the business of training you, not drowning you. But it's an interesting thing we have to do to be able to go out and do oceanography off of oil rigs. Okay. I will also add, just from a more personal level, the operational environment out on these rigs, it can get very, very hot. It is a lot of heavy lifting. That's me after taking a picture of myself in a mirror in the changing room after a shift. I think I took that one down, not in the Gulf of Mexico, but off of Suriname, off of South America on the East Coast or Northeast Coast. It's a lot of hard work when you get out there. I am transitioning myself to letting the younger guys do the hard work, and I just try to support them as I get older. So let's talk about these systems and what Woods Hole Group has contributed to doing this. When we first were contracted to build a system for the West Auriga and several other drill ships, we started in a very basic way, envisioning that we would use acoustic Doppler current profilers. I do not know how many of you are familiar with ADCPs. A quick lesson would be that they send out pulses of sound in pairs of beams. So this one looking down would actually send out 4 beams in 2 orthogonal planes, and then listen to the echoes. And there'll be a Doppler shift in the echo, because if the flow, and I hope you can see my cursor, if the flow is moving along this way, this echo is going to be at a slightly higher frequency because the flow is compressing, and this echo will be at a slightly lower frequency because, given the angle, you're stretching it out. And if you look at the difference, you can get and assume that the flow here horizontally and here horizontally is the same. Do the trigonometry, and you can calculate at each of these different levels what the horizontal flow is. And since you've got 2 orthogonal vertical planes, you can get an east velocity and a west velocity at each of these different levels. So if I manage to put some kind of frame with a downward looking ADCP and an upward looking ADCP hanging off the side of this ship, I can get current profiles, which is what the ship is required to provide to NDBC to be allowed to operate. And so I could envision that I'm going to have to build some kind of a sled that is going to hold these instruments. I will have to have some kind of gantry to suspend it from. I'm going to need wiring to communicate with it, some way of bringing it up and down, probably a computer. And I'm going to need to be networked or something, because I have to deliver this data for my customer, all right, in near real time. So those are just to give you a basic idea of the parameters. And then we get into the specifics of how we're actually going to do that. We looked at, excuse me, just having a little bit of juice here. We looked at some early systems that competitors and other companies had built, and they're terrible. It's a fixed frame. You can see the picture here. We actually got to replace this one on another ship. The frame is barely over the side. There's no movement of an A-frame that would help get very heavy equipment over the side. The 38 kilohertz ADCP, that's sort of the necessary beast here, weighs, just the transducer weighs 600 pounds. You know, and if you don't have an articulated A-frame, we thought, you know, you're risking personnel because they're going to have to push this thing over and pull it in, and it's heavy. They're using air tuggers. Other problems with the system that most people were using is that, aside from being very labor intensive for launch and recovery, just the transducer was going over the side. So they had a very fragile, large diameter cable that they had to get down to the transducer, and the other end had to come up to a deck box. The thing had 50 conductors in it and was extremely susceptible to getting cut, broken, fish bite, a bunch of things. And it cost months and $10,000 to replace. They were using wire rope on air tuggers to lift everything up and down, and then they would feed this expensive, fragile multi-conductor cable in by hand and tie wrap it to one of these. It was an insane system when we saw it, and we just couldn't believe it. All these personnel safety issues. And then we understood why these get installed and the oil companies bought them. They are really, really cheap. We didn't go in for that, and have been able to sell a number of these systems. What we did was, well, you see this big disc? Under that is the 38 kilohertz transducer that weighs 600 pounds. We took the electronics this was a new version. We ended up with serial number 0. The electronics that had been at a deck box were now placed in an underwater housing. So you only needed a communication and power cable, 7 conductors coming up to the surface. Here's what's called a workhorse ADCP, 300 kilohertz, that is looking up. And what we wanted to do was replace that fragile external data and power cable. So, you know, with the UWA, we were able to do that. Here's the gantry sitting in a cradle, keeping things safe. I know I'm kind of skipping my bullet points here. The 300 kilohertz is tilted away from the ship and things like that. The downside is this is not really cheap. This is going to be an expensive system. Here's another view of it. You can see the transducer underneath, a couple of winches. And what we did, and you can see it a little bit in this picture, is we used electromechanical cable. There are actually conductors in these armored cables. So they're both the mechanical support and they carry the power and communication wires. So no more of this, you know, somebody having to sit on the edge of the ship, which is dangerous, and tie wrapping another cable onto wire rope. And you can see the edges of a couple of hydraulic rams. This A-frame is articulated and can move. There's a hydraulic power pack driving it, an operator control stand. And here's a view. This was the first one we built. I will show you the most recent one we built in a moment. But this should give you an idea where we've got these electromechanical cables supporting the sled. The instruments are here. You can see the baby ocean down here we used for testing at our fabricator. This A-frame can move up and down. So we could pull this in up near the shiv blocks, swing the A-frame back over the cradle in here, and then lower the sled back down to work on it and reverse the process to launch it when you need to deploy it. Much safer for personnel. You only need 2 people instead of a whole crew, and it can be done in a few minutes instead of it taking hours. Our next version, we went to a new kind of winch, added a level wind, used a thicker cable that had more conductors in it, in particular some heavier duty conductors. That helped a little bit. This picture is actually on the West Auriga. And then finally, in our most recent iteration, and I will show you a rig this is on in a few slides, we designed our own winch without the level wind, which turned out to be a lot of moving parts. And if you look at the grooves on the drum and in here, that's actually a single groove helical that the cable lays on. We don't actually need more than the 1 layer of cable because we only needed to get about 80 meters of cable on the drum. We're only going to lower our sled to about 35 meters depth. Unfortunately, we're 20 to 30 meters above water level, which makes things a little interesting. So we just needed a roller to make sure it didn't pop out of the grooves. So this is, in a sense, a level wind with almost no moving parts to maintain. That is the final product. That is the most recent version of our launch and recovery system for working off of these rigs. You can see the transducer of the 38. There's the underwater electronics, the tilt plate there. We don't, in this picture, have the workhorse 300 kilohertz. Here are the helical winches, shiv blocks, the A-frame that can be moved up and down you can't really see it, but the hydraulic power pack's there in the background. This is down in Houston, our steel fabricator. And this is really the state of the art when it comes to these systems. It remains difficult to get the customer to go for this. The people out on board like it because it's so much easier and safer to operate, but often it's the accountants who decide what to get because of price. That particular system was installed on this semi-submersible. This is the Helix Q5000. If you look up where I'm pointing with my cursor, that red A-frame is for an ROV. It's much bigger than our A-frame. Our A-frame is sitting up here in this tiny little spot. You can just sort of make out the yellow of the safety mesh on the winches in this picture, which I took one evening as we were doing installation. This is down in Texas. These things are huge. The platform up here, you could fairly easily drop a pair side by side of football fields on that deck. They're enormous. The crane here, which goes right out of the picture, has a lift capability of 400 metric tons. These are very big objects that we are working off of. Here we are during the installation. One of the young guys who works for me, who leads the field teams now, so I do not have to go out to sea. That's Eric Aronchik. You can see almost 40 meters down below this platform into the shipyard. But there are the winches, the A-frame, hydraulic power unit. We're getting ready to run hydraulic hoses and install electronics. Here we are closer to completed installation. I think I was standing up on the helideck, the helicopter landing deck, looking down to take these pictures. You can see from the back, looking over the side. It would be hard to tell in this picture. You can see the transducer plate, the underwater housing, other equipment, and this is the dock we were tied up to that's 30 meters down from this level. Another picture looking down, and if you remember the ROV A-frame, there's the corner of it. The system, of course, is not complete without a controlling PC to keep it. What I've been showing you so far is really the mechanical systems. but we also design the electronics. We design and write all of the software that does these things. So once we were done designing winches and A-frames and the skid mount and all of that, the shim blocks and all of that equipment, we had to take those electrical signals on the electromechanical cables and do something with them. So there's a small logger controller out on deck that is bringing in through serial ports the information from the actual instruments. There's wiring built into the ship that we take advantage of to get that to the accommodation space. Remember the 7-story hotel and office complex that is so tiny on all of these, but the computer is rack mounted somewhere in there. So the computer's down here. We've got a couple of monitors. You can see what's on the screen. All of this had to be wired together, and different conversions between Ethernet and fiber optics and serial communication and everything else to make it all work. I will not go into all of the details. We also split off the feed to one of the monitors so it can go into the closed circuit TV, and the data display can be visible around the ship, around the rig where people might need to see it. A little bit of a close-up. This is the Woods Hole Group software that controls these systems. This display software was actually something I wrote. Another one of our guys wrote the software, the firmware that runs on the logger controller that's doing some of the distributed smarts, and yet another person wrote in C# the code that's running on the computer that's sort of the glue that holds everything together and works with the information from the logger and sends real-time data off to places it needs to go to meet regulatory requirements, and puts real-time data where my display software can catch it. So an operator control panel for the displays. This I will explain in a moment, because we're going to see other displays like this. What you're seeing in the top panel, well, let me start with the right panel. Over here in red is speed as a function of depth. So up near the surface, it's going at about half a knot. As we get down to, say 1,500, in this case, feet, because we were working in the US Gulf of Mexico, and for whatever reason, they work in knots and feet, things are getting down towards 0. The blue dots are showing direction. So 0 is north, 180 is south. And because I think better about oceanography in meters, I made sure meters was shown on the right side. But this is a single profile from the instruments. What you're seeing here in these two panels is a time series of profiles. So we're going from 0 at the surface down to about 4,000 feet. There's a color bar to show speed intensity. So it's a little hard to see, I suppose, but it's a little faster here, a little slower here, not a whole lot's going on. But each of these vertical lines is another one of these profiles, speed, and then down here, direction. And what you're seeing down here in the direction profile is called inertial oscillations. I don't know if there are any physical oceanographers in the crowd, but these are a ubiquitous phenomenon everywhere in the world. They tend to be hard to see unless the rest of the ocean is fairly quiet. And we could see in this picture that nothing's really moving very fast. We're down near this part. I will show some slides later that have better examples of inertial oscillations. But if you think about it, at a given depth, say 3,000 feet, if I just go at a constant depth over time, what I'm seeing is a change in direction, all right? So that the flow is first going south, then it's going west, then it's going north, then it's going east, and basically at different levels. This is not the clearest example. I'm going at different directions at different times. I'm a little out of phase, but this whole construction, in a sense, is rotating And in the Gulf of Mexico, the period is around 25 hours. It's related to the latitude and the period of rotation of the Earth, but it's not the same as tides. All right. This is the CCTV display. They like this on the bridge. They like having tabular data like this along with the one graphic. They want to know what it's doing now. They're not as interested in the time history the way I am. But that's the display that we pipe around the ship so that anybody who wants to tune into the closed circuit TV can see what's going on beneath the keel. That's a basic rig system, hanging off the side with that A-frame and that kind of thing. Variations on a theme. This is a moon pool system. You can see a different sort of ADCP here in a sled. And this slides up and down rails, and then the cabling comes up, and again, it goes to a computer, and there's displays. This is a SolidWorks graphic showing a system we built that sat on the side of a vessel on rails, and a sled down here with the ADCPs went up and down. Roughly, this was, I think, 60 meters up and down. And we came up with a way to build these rails in a modular way. I actually went out just by myself to install this, worked with a rigging crew on, this was the Pacific Santa Ana, a drill ship. And we had a very good design to make sure that these rails could be assembled as we were lowering them, and we'd put the next section in and the next section. And we had to have this crossbar hit a couple of pins that were about 20 meters below the water line. Yeah, about that. Couldn't see them. ROV wasn't available. We got the whole thing in only 3 hours because we had thought ahead to make a deployment design, not just the equipment design. And we landed on those pins on the first try. The riggers were just tremendously impressed. Came up, we just did it in the morning and then all went into the mess deck and had lunch. It was great. We're not always putting systems on a rig. Here's an example of a deep ocean mooring. This is one we designed. It's been in the water for, I think, 7 or 8 years now in the Gulf of Mexico in about 1,400 meters of water. We service it annually, pull the whole thing out, take it apart, put it together, replace all of the cables and ropes and things like that. This is near a platform called Mad Dog, 3-meter surface buoy of our own design. There's some MET instruments on it. There's an ADCP looking down and getting the near surface. This concoction is made out of nylon on this side, which is a little heavy, and polypropylene, which is a little light. And then when the winds or currents blow this or blow it back across, this length is such that it doesn't foul on either the top or the bottom, and it doesn't tangle. This is a fairly standard design that I think Woods Hole Oceanographic people came up with some years ago, but it makes for a very robust mooring. There's more ADCPs at about 500 meters down, one looking up, one looking down. There's a further measurement here about 30 meters off the bottom. Railway wheels as an anchor that's sacrificed each year. Acoustic releases. This is 900 or so meters. The picture is not to scale, but this has been working great and returning data in real time via satellite rather than through an internet connection on the ship. And of course, the internet connection on the ship is through a satellite. And a very successful approach to this kind of thing. We actually get much better data quality off of the mooring than we do off of one of the rig systems where the hull can interfere with some of the measurements or the risers under the hull. This is at some distance from the platform, and that helps a lot. So here are some of the characteristics of these systems in general. So data delivery in real near time. We have to be on a secure network or a satellite connection. We're doing an FTP to NDVC to ourselves so we can monitor data quality. We have remote access through the satellite and through the network so that we can maintain and work on these systems without actually going out to sea if possible. There's the local distribution, either a website like the mooring or the CCTV. customer needs, so graphics and text, data export so they can do their reports. We have found often they're only putting these systems in because they have to, the government insists, and then as soon as it's on board, it becomes invaluable. We're constantly getting questions and how can I do more with this, and it's so helpful and things like that. But the people who are actually operating the vessels have found being able to know what the current is doing at different depths below their keel when they've got a kilometer or 2 kilometers of meter diameter riser hanging from the ship during drilling operations is invaluable. They love it. We're getting in position and heading from the navigation system on the ship, or we've integrated a GPS and a compass into the system. So we think we succeeded, but remember back at the beginning of the talk, this mandated program that measurements must be made and communicated into a public database. And the question then became, are the data in the database any good? And about 10 years ago, a consortium of oil companies operating in the Gulf of Mexico, the consortium was called Deep Star, commissioned a study, and we proposed, our proposal won, and they wanted to know the first 5 years of the program, was the data in there any good? Could you use it? Because people had just been putting it in, and there was no mandate for data quality, just the mandate that thou shalt return measurements. They don't need to be any good. You just need to give us measurements. Not the best way to run things, but there you are. So anyway, we won that project. We developed a bunch of software tools. We built a database, and we worked on the project data, that 5 or 6 years of data, for about a year. And we discovered that unfortunately a large portion of that NTL database was compromised, but often by metadata errors, some of which could be corrected. Before they insisted that your system have a GPS feed, rigs were manually putting in latitude and longitude, and you'd have the position wrong. They would get confused about installing the current meters and essentially get their compass wrong or their beam direction wrong, and you'd end up with the right speed but the wrong direction. Instruments were left in the water when the rigs moved, so it would look like velocity data of the ocean, but no, it was the velocity data of the ship. And there were other problems with it. And by large, I mean 30 or 40% of the data in some cases were compromised. And the trouble was there was no way to know which measurements were compromised unless you looked at all of the measurements, which made it a rather problematic database until we got into it. So here's an aside before I tell you what we found. We were using public data, but Deep Star was paying us to clean up and make an analysis, and that clean data was at the time proprietary. We couldn't share it with anybody. The clean data were not public. There is an ongoing study now commissioned by in the US, the National Academies of Science, Engineering, and Medicine, that we again won the bid and are doing, where we're doing quality assurance, quality checks on the rest of the data all the way up from 2010 to now. We are not, as we did for Deep Star, looking for special features, extreme events, or anomalies. We're just cleaning it up. But this will be a public database, and we had a long conversation with the Deep Star Consortium, and the first database will now be released publicly. But this leads me to a thing where oil companies are very dedicated to secrecy. They like their data. They do not like to share it. And I have a story for you. Some of you may recognize this. This is the Yucatan Peninsula. Up there at the top is the small town village of Chicxulub. And some of you may be aware that that's where the meteor that took out the dinosaurs 66 million years ago impacted. All right, so here's the Yucatan Peninsula shown approximately 66 million years after the impact of a 10-kilometer bolide. The crater, depending on what you consider the edge, is 180 kilometers across, or 300 kilometers across, and about 20 kilometers deep. In 1980, an explanation for the disappearance of the dinosaurs was proposed by Louis and Walter Alvarez, father and son. Louis won a Nobel Prize for some other work in physics. His son, Walter, was a geologist, and they had noticed, as others had, but they made more of it, that at that dinosaur extinction boundary, Cretaceous, Tertiary, there was a layer of iridium globally. You find this iridium layer everywhere you look if you can get down in the stratigraphy to 66 million years. And the observation is that iridium is relatively rare on Earth. It's relatively common in space objects, right? Asteroids, comets, things like that. And their theory was there's a global layer of iridium because a large asteroid hit the Earth, and in the resulting crash and spread and disaster, that iridium was spread worldwide and left a layer that's detectable. Well, they got laughed at a lot. I don't know how many of you know this history, but they were just called crazy. Everybody dismissed it. And one of the critiques was always, yeah, right, sure, where's the crater? And, you could say, look, given plate tectonics in 66 million years, there's no reason the crater has to still be around. It could have been subducted. Then in 1990, this crater, Chicxulub, was found by oceanographic geologists, and it had the right date, and it was the right size and everything else. It was found in 1990. The Alvarezes were vindicated. This is relatively accepted at this point as at least contributing to the demise of the dinosaurs, if not being the only thing. And perhaps it was the only thing. But coming back to secrets, Pemex, the Mexican national oil company, had found that crater in 1970, but that was their data and they wouldn't tell anybody until somebody discovered it publicly. So that was the answer with the oil companies keeping their secrets. So it was, well, we already knew that, found it in 1970, didn't think anybody would care. And here had been this raging scientific argument about the demise of the dinosaurs. But no, they didn't release the data, even though there's no oil anywhere near the crater that would help them out. So anyway, remember this slide. Was the program a success? This is an example of the metadata errors. And so here's the Gulf of Mexico. These contours are showing sea surface height again. So you can see these blue lines are going, from a measurement point are parallel to these contours, showing appropriate directions for speed for current direction and speed near the surface, except this red one, which obviously is wrong. And this is just an example of an error, in this case, in the ADCP beam orientation. Their software is assuming that beam 3 is pointed along the ship, and obviously it's pointed across the ship, and you get the wrong answer. And unless you look at all of this other data and this independent satellite map of sea surface height, you'd never know this is wrong, because it's a perfectly good speed measurement. It's high quality data, but it shows entirely the wrong direction. And there's no way to know that without looking at other data. So that's just an example. But those were the kind of things we were able to correct by looking at other data. So despite the problems, that 34 to 40% error rate, we were able to reduce that and correct a lot of the data. Net result, in the first 5 years of that program, 151 site years of good data. There is reason to believe that here we are in 2020, there's in excess of 400 site years of good data now for the Gulf of Mexico, publicly available. And that those data contribute to our understanding of how the Gulf of Mexico works. They can be used to support safer operations, better vessel designs, oil spill tracking, severe weather response, search and rescue, all of these good things. So this is an important database. And I would say that the in that sense, it was a success. But remember the quote I gave you at the beginning. In looking through all that data, we found 560 energetic events in the flow that were absolutely not expected. All right, strong near surface currents with this enormous shears, nearly 300 of those. Midwater jets, I mean, the ocean just zooming along at some depth with no surface expression that was going on. No way to know about it unless you made the measurement. Strong inertial oscillations, and these enormous slab flows. And I'm going to show you some pictures of these. So here's a strong near surface current with high velocity shear, and you can see, remember the speed and direction profiles. So this is top to bottom is depth, color bar for speed. All right, so you're looking at 2.5 knots up here and dropping to essentially zero within 200 meters. Direction is down here, and basically it's all kind of common direction, slab flow like. But this is something, you know, who knew you were getting these high velocity shears? Midwater jets, no surface signature. Time is going along this way, but here we have these very strong currents modulated by inertial oscillations. That's the modulation you see going across. That's not a tidal signature. That's an inertial oscillation signature. But this jet is going along at just under a knot, all right, 40 centimeters a second, and nothing happening above that at the surface. So a hidden hazard if you're operating there. Strong inertial oscillations, we're down at 500 and 600 meters, and this is pulsing in and out. Here is that direction signature. And just as an example, if you were looking at this vertically at some point, you're going, in this case, north, and then you're moving into west, and you can see how you're sort of, as you go up in the water column, you're turning the direction you're going. But also if you're going across at constant depth, you're turning over time. So you can think of these structures where at one level you're heading east, but at the level just below it, you're heading northeast. But those two vectors are themselves turning around over the course of 25 hours. So it's an interesting flow and an interesting phenomenon, but very strong here. So I come back to, there's no substitute for making a measurement. And the most exciting phrase in science is, that's funny. We find things as engineers, we enable finding things that we didn't expect. And that is where cool stuff happens. I will leave off this talk with just a couple of fun slides. I spent time at the beginning telling you how big a drill ship is. I'm standing for this picture on the bridge wings looking aft. You remember the size of our A-frame, quite a bit bigger than me? That's it back there, and that's only halfway to the back end of the ship. How far down to the water? Well, this is nearly 3 meters across. We're looking down a long way, and that's something we had to be aware of in our designs. It is traditional, at least where I come from, and which is Woodsole Oceanographic some time ago, to end all talks with a sunset picture. This is Mount Fuji outside of Tokyo as I was, my plane was descending, sunset with Mount Fuji in the background, also just before missing my connecting flight to Singapore. And finally, since I am talking from the Northern Hemisphere, but Guayaquil is just into the Southern Hemisphere, you get 2 sunsets from me. And this one is north of Mauritius in the Indian Ocean, a place I spent several weeks doing an install some years ago, and part of the Southern Hemisphere. And on that note, I am done, and I will entertain your questions. And again, thank you very much for having me as part of this event. It was great.
Thank you, Todd. thank you for your presentation. In this space, we're gonna dedicate it for the question, if there are, of the attendees, and if they're not, I proceed to finish for today the event, the new era of oceanography. And maybe let me read if there are questions. No, I guess.
I think the have question.
Okay. Who is?
We don't have question.
Ah, okay. We know. Yeah, okay. Well, Todd, thank you very much for you accompanying us with your presentation. We enjoyed it for real your presentation. It was awesome. For the science develop, and thank you for the time you in this meeting. Well,
I would like to thank you all very much for setting up this delightful symposium. I have been enjoying the talks all week, and quite an accomplishment.
thank you. Well, for today is finished the new era of oceanography. Tomorrow we'll continue with the last day of the new era of oceanography. So in the link will be sent to your respective emails, and well, see you around tomorrow, and thank you two for your attendees.
I look forward to it.
Thank you so much. Bye bye.